So when we look at the periodic table that I have here, this is a periodic table that I found somewhere on the internet. And I kind of like it because it does show, again, the majority of the elements being metals, the minority being nonmetals, but it does include also some of the metalloids. Now, for what I'm doing in here, it's either a metal or a nonmetal. Okay? In AP Chem, it's either a metal or a nonmetal. And the thing that separates it is this stair step that we see along there. So if it's on the left side of the periodic table or left side of that stair step, and you have that stair step in your periodic table as well, that's a metal. If it's on the right-hand side, it's a nonmetal. Now, this periodic table also shows that hydrogen is a nonmetal. The reality is it behaves as a metal and a nonmetal. So that's kind of one of the, I don't really put that in a category. Now, if this were a periodic table dealing with organic chemistry, oh well, this is going to be a non-metal all the time. But when we talk about acids and bases, hydrogen's a metal. So don't freak out about it. What I want you to know about the definition of a metal and a non-metal is metals give away their electrons, non-metals take on electrons. That is the biggie for determining who is metallic and who is not. All right, so here are a couple things. Again, the majority of the periodic table is made up of metals. Metals are generally good conductors of electricity and heat. The biggies are like the copper and silver and gold. Those are the ones that we primarily use for conducting electricity. Heat, yeah, these things do move. Metals heat up really quick, and they also lose their heat rather quickly. Also, if you look at a freshly cut or cleaned metal, it looks really shiny. Generally, the ones that don't look so shiny are oxidized, and you can clean those up pretty easily. Also, all metals, except for mercury, are solid at room temperature. And if you look at the periodic table, and I think I even have it on my periodic table that I gave you, you'll notice that if it's black, the symbol is black, what that means is that it's a solid at room temperature. If it's blue, then that means that it's a liquid at room temperature. And if it's red, then that just means it's a gas at room temperature. It doesn't mean that if it's black, it's a metal. If it's red, it's a non-metal. And if it's blue, then it's a metalloid. That's not what that means. It just means black is solid, red is a gas, blue is a liquid at the temperature we're experiencing right now. Yeah, gallium will melt in your hand. Yeah, but typically, since your hand is warmer than the air, it's a solid. Yeah, we don't. Yeah, it's like M&Ms. Oh no, it doesn't melt in your hand. It melts in your mouth. That's an old M&Ms. They melt in your mouth, not in your hand. That was a promo that they had when I was a kid. Well, yeah, if you hold them like this forever.
Yeah, mine should never melt my hand.
All right, nonmetals. On the periodic table, again, the one that I gave you, it's that blue section, but it's the one that's to the right of the stair step. These nonmetals, generally speaking, they are very poor at conducting heat. They're very poor at conducting electricity. That's a generalization among that. And most of the nonmetals at room temperature are a gas. Not all of them, but most of them. And there are some weird differences in terms of properties with nonmetals. Like, for example, diamond is a nonmetal. Okay, it's made up of 100% carbon. And carbon, which we'll talk about later on, I believe it's after winter break, these are held together with very strong covalent bonds. So it's the hardest naturally occurring substance. Where if I look at, say, phosphorus, and we've been messing with that in the lab, the matches, it's very brittle. So you got something that's really, really strong and something that's really, really brittle, and also you have things that are gases. So it's all over the spectrum with nonmetals in terms of what it does or how it's composed. What's that? Not much. You hit it right. Of course, if you have a wedge and a force, a small point, then it does some amazing things. But I don't go and break diamonds in front of you all. All right. Again, I already mentioned that they're generally poor conductors of heat and electricity. Carbon's very interesting. And that's why it has its own branch of chemistry called organic chemistry. And it is all over the spectrum. I mean, it's what makes up the diamond. It also makes up the lead in your pencil. So it can be really, really hard or really, really soft. So carbon's a nice thing. Metalloids, this is the only time I'm going to talk to you about metalloids. Generally speaking, they behave more like nonmetals than they do metals. Okay. In other words, they're not very good conductors of electricity by themselves. Like silicon is used in silicon chips, but it also has to have some boron mixed in with it to make it a good conductor. So by themselves, they're not very good conductors. However, yeah. And again, metalloids lie right on that stair step, and they go back and forth on there. But yeah, that's all I'm going to say about that. So you will not see metalloids on the test. Forming ions, this you will see on the test. When we talk about metals, in general, for every metal that we're doing in here, it loses electrons and becomes more positive. For nonmetals, in general, now this isn't in general, they gain electrons. Okay. When we talk about the most common charge, we're talking about the 3 or less or 5 or more. So if a metal has 3 or less valence electrons, it's going to lose those 3 to have the same electron configuration as its nearest noble gas. If it has 5 or more valence electrons, it's going to gain to have 8 electrons, so it'll have a negative charge. So that's what I want you to define a metal by a nonmetal. We talked about representative elements already. It's those A groups. So when we look at the periodic table and you see those S and P orbitals, that represents the representative elements. Like that represents the representative elements. Patterns for transition elements and ions. When we talk about, and this is kind of a little exception to the rule that we had with electron configurations. This only happens in these 2 rows. When we look at the periodic table, what I'm about to talk to you right now, it only happens in these 2 rows right here. There's what's called special stabilities. Okay? And what that means, and I have it in the notes, if I have a half-filled S, in other words, how many electrons can we have in the S orbital? 2. So if I have a half-filled S, how many is that? 1. So what that means is I can take an electron out of the higher energy, in this case 4s orbital, and place it into a lower energy 3d orbital to cause the d orbital to either be half-filled or full. Okay? Because there are special stabilities with half-filled and full orbital sets. Okay? So let me give you those exceptions, and then I'll do a couple examples. Okay? And again, it only happens to those 2 rows in the d orbitals. And what we never can do, we can never take electrons from a lower energy level, which in this case is 3d, and move it into the 4p orbitals. We don't ever move electrons to higher energy levels without it being excited. So let me give you an example here. All right, and here is what I just mentioned. So if you highlight this area right here in your notes, very, very important. Okay. So there's special stabilities that occur when you have a half-filled s orbital to create a half-filled d orbital. That's what this first one talks about. So we have a half-filled s, which means that we only have 1 electron in the s orbital, whether 4s or 5s orbital. And then half-filled d, how many electrons are in half-filled ds? 5. Good, because the max is 10. Here's another exception. Or completely filled, and that should say like a d orbital. So completely filled d orbital, and the f orbitals are half-filled. So we can go half-filled s to make a half-filled d, or a half-filled s to make a full d, full. Or we can empty out the s orbital, take both of them out, to have a half-filled d or a full d. Okay. So it's all about taking from the s, 1 or 2, to have either half or full d orbital. Let me give you an example. Okay, I'm going to draw and I have chromium on here, but I want to show you with the arrows. And again, this goes against the convention that we discussed, and I did not want to talk about it last topic. So if we have chromium here, we have argon, and it's in the 4s, and we have 3ds, 1, 2, 3, 4, 5. So here I have that. Let's say that. And then chromium has 4 electrons. It looks like that. All right. So this is how the electron configuration would have looked last topic. However, the reality is, and I didn't want to mention it before, but it's actually going to take one of these electrons from the 4s orbital and move it to the 3d. So, and again, it doesn't matter if it's up or down there. But in this case here, this is a happier element because now everybody has their own room. And we're able to take that electron from a 4s orbital, higher energy orbital, to a lower energy level, and now everybody has their own orbital. So it's half filled. Okay? So that's one of the scenarios. Okay? Another scenario is if I look at, say, copper. Let's change the Cu, or Cr to Cu. So now we have this scenario. Oops, let's put an electron there. Okay, so here we have our scenario with the copper as we would have written it last time. But there can be, we can take an electron from our higher energy level to have a half-filled S and a full D. When you fill up an orbital, that energy level is very happy that that orbital is full. So by doing this, by moving this electron from a higher 4s orbital, higher energy level, to here, now we've completely filled up all the third energy level orbitals. The S's are full, the P's are full, and the D's are full. So there's special stability there. Okay. So if you can look and say to yourself, and again, it only applies to these 2 rows. The 2 rows down here, it only applies to those 2 rows, then that's the only time that we're ever going to talk about it. So once we get into the other d orbitals, what's that? I'm going to delete that. Okay, let me zap these first, and then I'll show you. That would be easy if I just did that. So much more fun. All right, so the question was, why does it only apply to those 2 rows? Once we get to this row here, what are we introducing? The f orbitals. Okay. Yeah. So we're not going to move electrons from the f orbitals into the d. So that's why these 2 only apply, is because we don't have any f orbitals. Say that again.
How many underlines go in the F orbital?
There would be 7 dashes for the f's. Yeah, but we don't talk about the g orbitals. We don't say the g's. The g's, they're out there. All right, and we'll have some more practice of it. Now, here is the one and only example that I'm going to ask you about for forming an ion with a transition metal. Okay. Now, after this, we're going to be going gangbusters on forming ions that are in the representative elements. But here's one of the examples. So we have iron that goes from a +2 to a +3 charge, and notice that here it has the half-filled stability, and going from a +2 to a +3, we would remove that electron. Okay. That will not be on the test. We will talk about that in AP. All right. So I just wanted to let you kind of see how these things work out, and that, yeah, it still does happen if it can. Now, if we have a weird number of electrons, we can't force it to be half-filled. We can't move electrons out of, let's do this. Let me give you an example here. Let's say that I'm looking at regular iron, okay, just regular iron. So if I have regular iron, and I have my configuration here, let's go 4s, 3d, 1, 2, 3, 4, 5, and say 4p. Okay. What I'm not going to be able to do, how many does iron have? 6. Okay. here's what we cannot do. We can't say, oh, we could give everybody their own orbital by moving an electron over to here. That doesn't work. Okay. So if it looks like this for neutral iron, and that's the way neutral iron looks, you leave it. Okay. You leave it alone. If it doesn't work, if you can't have a half-filled S or a half-filled D, don't mess with it. Does that make sense? And don't get creative and start moving. Well, I'm going to put these over here in the 4P, and then when that one gets half-filled, I'm going to bring it down to the 5S. Don't do it. No matter how tempting it looks, don't do it. All right. So the homework, all of those look good. I do want to work out one. Where is it? That was yeah, here it is. So 2E, we'll write out 2E because this will be the last time you see it. Write out the correct electron configuration for the element copper when it has a +1 charge. Okay, so copper, and I'm going to do the modified. I like this. This is a nice little hybrid. 1, 2, 3, 4, 5. So let's say it's got 1, 2. How many does copper have? 9. What's the matter? Okay, so that's the way that copper looks in the good old days. The reality is, whoop, where'd it go? Oh, wow. The reality is, it looks like that when it's neutral. So where would we take the 1 electron from to give it a +1 charge? 4s orbital. Good. So we would remove that electron to make copper a +1. Okay. If you feel good about that, you'll like it in AP. Okay. So there is your copper +1 because we took that, which was neutral, from the higher energy level. Okay. There's neutral. There's +1. Okay. Wait, what? What's the matter? Okay, this is what it was back in the day, a week ago. So there's neutral copper, as I taught you in the last topic. The reality is that 1 electron moved over. So there's our special stability where we have a half-filled S and a full D. If I say +1, that means I take an electron away, and I would take it away from the +1, or the higher energy S orbital. Okay. All right, so do the other 2s.